Hi, my name is Ted Cross, and I'm a technical advisor with Nova Labs. Today I'll be presenting our paper, Benchmarking Operator Performance in the Williston Basin using a predictive machine learning model. Why benchmark performance with machine learning? First, performance relative to peers is of critical interest to operators looking to improve results or acquire underperformers, and also investors, such as non-op working interest holders, private equity investors, hedge funds, etc. And what are the standard criteria used for peer selection in a benchmarking study? There's geographic proximity or overlap of acreage, company size, and if the operator is doing the benchmarking, whatever makes you look good to investors. Why use machine learning? First, it limits bias relative to hand selection methods. It can also estimate relative rock quality and provide a baseline expectation of production, which is the prediction. So for this study and this example of a machine learning model for benchmarking, we're using the Bakken Three Forks play of the Williston Basin of North Dakota with data from the NDIC, which provides high quality publicly available data. For input variables, we have proppant and fluid volumes as well as stage counts. For spacing, we have distances to various neighbors and overall neighbor count. For timing, we have parent count, time, and distance to parent wells. And for the geology variables, we used a variety of well logs, mud log gas measurements, and structural tops. Not included, we just want to note, no operator included as a categorical. That can really kind of defeats the purpose of a study like this, because the model will actually kind of solve for how what's special about the operator or not special. Second is we have no latitude, longitude, county, or area because we want the model to be learning from the geology to allow benchmarks that aren't just directly adjacent but are still in similar rock. And third, we do not have any post-drill operational data. These are just kind of pre-drill or at the time of completion data. For our model, we used a decision tree-based modeling approach, specifically extremely random trees, which are similar to random forests. And the way it works is that the model builds a series of trees where you start from, all the data in the basin is kind of basically piled in one group, every single well. And you can imagine that that set of wells will have, let's say, an average 1-year cum of 90,000 barrels of oil. The trees then split the data according to certain input features or variables, like in this example, water saturation greater or less than 25%. And then they split them further according to other variables. And at the end, you're left with a set of, sets of wells in groups in these leaf nodes, terminal leaf nodes, that then have other different average production variables. So here we have a group of 72,000 barrels. Here we have 120,000 barrels, and that's different than that 90,000 barrel average. And the idea is that the model will build thousands of these trees that are using different variables that are split at different levels, that are different levels deep, that have that are put together in an ensemble that will actually create a pretty robust model that avoids overfitting. But the overall goal is for it to discriminate production values so that it can identify high producers, low producers, and everything in between. These models, they can handle both numerical and categorical variables. Formation would be an example of a categorical. We also will split the data randomly into training and test sets, which I'll show you a little more on that in a minute. The target, even though right here I've just listed in this kind of cartoon tree, I have just 1-year cums, we actually target a 24-point vector of monthly cumulative production going from 30 to 720 days. So rather than a single target like 365-day cum or EUR, this allows you to actually get the shape of the curve accurate, which is essential for economics and evaluating decisions. In the course of building our models, we also derive Shapley values, which explain the model predictions, and we use those to derive a rock quality index called geoSHAP that we'll be using heavily in this paper. So as mentioned, we split the data randomly into 80% and 20% training and test groups. You can see they're both well distributed around the basin. And over on the right, I have the error scores that we have for each year of when the well was fracked. And you see, for the most part, the test scores are, the blind holdout, are stabilizing in kind of the upper teens to low 20 percentages, which that's pretty good for a regional public data model that's forecasting a vector of production. Okay, so now we'll kind of transition into the benchmarks that we're using in this paper. First benchmark is geoSHAP, and you can think of it as essentially a summarized rock quality index in the eyes of the model. So the way that this works is we start with raw logs, tops of geochem. We extract values and summarize them according to the zones that our model picks. That generates a set of geology variables. In this case, we had over 400 that we reduced through a principal component analysis to a set of 5 features that were then input into the model. We then extracted Shapley values from those that we then sum over well, IP day, and fluid stream to get geoSHAP. And I know that's a complicated workflow for a single slide, but if you want to get some more detail on that, we have an entire paper on that subject. So just go ahead and look up that paper. But if you just want to look at the map just to kind of verify how this rock quality index is doing at measuring relative rock quality, you can see that in the dark green we have the highest rock quality, in the red it's the lowest. So we can pick up things like the Nesson anticline, the Antelope anticline, the Fort Berthold hotspot. We have the partial Sanish field. So feeling pretty good about how the model is doing relatively at assessing rock quality. And these geoSHAP values, they're available for every single well that we put into the model. So if we use that geoSHAP, and here I've put that geoSHAP on the x-axis, so green is over here on the far right, red would be over here on the far left. It correlates strongly with actual production. So here I've broken out by the year when the well was fracked from 2011 through 2018. We have that rock quality index, the geoSHAP, versus the actual oil, and I'm displaying both as a percentage relative to average. So you can see we have the average geoSHAP value with the vertical line, and the average production value with the horizontal line. And every dot here is a well. So these are all the wells that were drilled from 2011 to 2018 in the basin. And I've colored them by the proppant in pounds per foot. So that's the most important completions variable in the eyes of the model. And so it's responsible for a large amount of essentially the additional dispersion that's not purely by rock quality. So you can see generally there's a nice strong correlation between the geoSHAP values and the actual production. It's slightly convex upwards. You can also see that originally, back in 2012, 2013, you had a lot of wells that are falling below average, and those are wells that are drilled with small and completed with small completions designs. As you make it out to 2018, you see most of the wells have moved above that average line, which is reflected in the proppant in terms of pounds per foot values. Also, just the total dispersion you can see has decreased from 2013 out to 2018, and that's because operators are converging on designs through time. So previously what I was showing you was aggregated at the well level. Here I'm showing you aggregation at the operator level. So every shape over here on the right, that is a specific operator. I've labeled one EOG here with the vertical bar there. So again, we have their average rock quality on the x-axis and their average production on the y-axis. And you see that there is a nice strong linear or potentially slightly convex upwards trend across the data set. I've also sized the operators by the well count. So you see most of the bigger operators are falling pretty neatly on the trend. EOG, as far as anyone who has standout performance, is by far the biggest operator, which not really a surprise. Small operators with wells that are, with less than 50 wells or 10 wells, something like that, they can have small sample size effects like operational execution issues or variation, geologic variability, like, they just hit a nice little hotspot or some natural fractures and model error. So we're going to investigate using some model outputs why EOG might be outperforming their peers so notably. So we're going to break out their performance through time and see how their outperformance changes across the years, as well as what wells were they actually drilling across the years. So I've pulled out the kind of that same chart that I just showed you of actual oil versus geoSHAP for 2013, 2015, and 2017. And then I also have on the right side where they were completing wells, as well as those have been labeled with the geoSHAP. So you see in 2013, EOG is crushing it. So they have much higher rock quality than most everyone else in the basin, and they're also producing maybe 100% relative to peers, 100% greater relative to peers with similar rock quality. And if you look over on the right, they have a lot of wells that they're drilling in the partial Sanish field, and then some others in kind of the Ness and Fort Berthold area. So really strong production areas of the field. As you move over to 2015, you see they're stepping out to the edges of the partial Sanish field, and they have shifted both to the left, reflecting lower rock quality, and also down, reflecting less outperformance. By 2017, you see EOG is actually kind of sitting in the middle of the pack. And again, they're kind of drilling, marginal rock quality or average rock quality wells on the whole, and their performance relative to peers is just about average. And why might this be the case? I mean, we have the geology going on over there on the right. That's one explanation for why they're moving over to the left. But you can also see that they were kind of really early to large completions compared to peers. So actually 2013, 2015, 2017, they were over 1,000 pounds per foot for each of those years. And actually, if you look at this, you can see that the crowd of their peers is kind of moving up, reflecting that everyone else is kind of learning that upsized completions will get you a lot more oil back. So I want to emphasize, I just hypothesized that their outperformance is due mostly to completion design. So they're using big jobs in good rock. So that is something that is known to the model. So the model knows the completion designs that EOG was using. So if that is what's responsible for their outperformance, then the model should be accurately predicting their production. So we're going to turn to a second benchmark here, which is the model prediction, which now I have the predicted oil on the x-axis rather than the geoSHAP. So we have actual versus predicted oil. And we see here EOG is falling just about right on the y=x line, maybe just slightly above it, but nowhere near the outperformance that you're seeing on the actual versus geoSHAP charts. So the dispersion that you see kind of around that y=x line, that is a result of a couple items, all of which are essentially, for us, known unknowns. So we know that there are post-drill operational choices that are not making it into the model, things like lift type, choke management, pump size, etc. There are proprietary completion designs that haven't made it into the model because they're not in the public data set, so things like diverters, cluster spacing, etc. And then there's local geologic detail, which is in some ways it's unknowable. So things like, are you hitting any natural fractures? Are there any kind of little local migration traps or anything that are enhancing your well saturation that are kind of below the resolution of the vertical well or pilot well sampling? So if we turn to another group, we can kind of investigate this benchmark a little bit more. So we'll see here there's a crowd of operators that are in this kind of 17 or so barrels per foot production prediction, and we have a marathon in that big kind of play button falling near the bottom of that group. So it's falling below the line. So our model is over predicting what their actual performance is. So let's take a look at what might be driving that. So first thing that we're going to look at is we're going to add in the predictions through time to see if we can get a little more resolution on what might be driving that model over prediction. And so here we have a similar chart to what I was just showing you, except now I'm coloring the dots by the IP day for the prediction, and this is all looking at cumulative oil rather than rates. But marathon, you see play button at IP 30. That's where they start off, kind of above the line, performing higher than the model prediction. By IP 720, you see that play button has made it below the line, so they end up falling significantly below the model prediction. And as far as the major operators in the basin go, that's the most kind of distance traversed relative to prediction through time. And so since this is, a shape of the curve issue, essentially, it may be that operational choices are the explanation. This plot here, these are all operator averages. If I skip ahead here, now I've broken it out according to individual wells. So these are all the wells that Marathon has drilled through time on the left, and all the wells that EOG has drilled through time over there on the right. And I've shaped the well by the year that it was drilled. So one thing you can definitely see here is that many Marathon wells, especially from 2016 and later, so that's plus sign, X, that, and then the kind of the 2 stars. You have a lot of those that are starting over here and significantly overperforming our model prediction, and then they're kind of crashing back down left through time. Whereas EOG, you see that the wells aren't traversing nearly as much distance through time. You see that EOG has a lot more wells here that start over predicting and end start overperforming and end overperforming, which is more what you would expect, due to geologic variability, model error, or maybe some of the other, maybe better, diverter usage or something else might be responsible for that. But Marathon, by contrast, a lot of wells that are having kind of that shape. And let's dig a little bit deeper into one of those Marathon wells. We'll look at the Brush 24-8H well, and it starts off here. So big time over producer compared to our prediction, and ends up there, slightly below our prediction out at IP 720. And I just pulled up the NDIC well file for this one, and just got a couple little pieces of information. First, it was IP tested with a large choke on September 6, 2017, with an ESP installed 65 days later. Both of these could be accelerating production. Just who knows whether their IP test was, who knows what choke they're actually using to produce these in the early days. But this kind of, both of these are suggestive of kind of operations that might, accelerate that production to the early days. Okay, so conclusions. First, machine learning models can provide powerful, minimally biased methods of benchmarking operator performance. It's really an alternative method compared to traditional hand selection. These methods can be used by operators, investors, service companies, government agencies, universities, really anyone with access to sufficient data and machine learning model building expertise, which is becoming increasingly common, and there's more and more off-the-shelf tools that can be used by non-experts. So we looked at 2 benchmarks today for performance. Benchmark 1 was geoSHAP, and that is the summarized rock quality that allows comparison to wells and peers that have similar rock quality. And we looked at EOG's performance relative to peers, and came to the conclusion during this talk that their outperformance is due mostly to large completions designs, which they were much earlier to the party on that one. Second benchmark was the model prediction. And that provides a baseline of how the operators are performing on the known unknowns, such as operational interventions. And Marathon's early overperformance and later underperformance relative to model prediction could be a result of artificial lift practice or choke management, just kind of based on that hypothesis that we threw out about big ESPs and wide chokes. Model building is an iterative process, so hypotheses generated by these benchmarks can lead to new data collection and model rebuilds, followed by new hypotheses. So you could take marathons, take this idea that maybe it's the fact they're installing ESPs early, turn that into a piece of data, add that into the model, and that transitions then from a known unknown to a known known. And you can see how that affects the model prediction and whether that resolves kind of that outperformance or underperformance. And I do want to emphasize here before kind of pressing the end here that just because someone is outperforming or underperforming on an actual production basis doesn't necessarily mean that they're outperforming or underperforming on value. It could be that any of the choices being made by these operators, depending on their costs and preferred economic metrics, may be perfectly valid. That's just up to the operator and the investor. But having tools like this can certainly help with benchmarking and evaluations to help you actually decide on the relative value of the choices available to operators. So thank you for listening. Please send us in any questions. If you have them, we'll be happy to answer them. And again, thank you.